All right, if you're in multivariable calculus, you know that some problems can be, well, a total slog. Today we're going to talk about one of the most powerful and honestly elegant shortcuts in your entire toolkit, Green's theorem.
At its core, the whole theorem is built on this one, surprisingly simple idea. Just think about a fluid swirling around in a container. The theorem basically says that the total spinning feeling you'd get if you walked around the very edge of that container is exactly the same as adding up all the tiny little microscopic whirlpools happening at every single point on the inside. It's a wild idea, and it's the key to everything.
So let's dig into that. Green's theorem creates this amazing link between two kinds of integrals that, at first glance, seem like they live in totally different worlds. It connects what's happening on the one-dimensional border of a shape to what's going on across the entire two-dimensional area it encloses.
Okay, let's get our two main players straight. On one hand, you've got the line integral. This measures something along a closed path. Think of it as the big picture macro effect you get from walking the entire perimeter of a park. On the other hand, we've got the double integral. This adds up a quantity over a whole area, kind of like summing up the value of every single tiny point inside that park. It's the sum of all the micro effects. Green's theorem is the bridge that connects them.
Now let's get to the formula itself. And look, I get it, the formal equation can look a little intimidating. But trust me, once we break it down piece by piece, you're going to see it's just a mathy way of saying that simple spin idea we started with.
So here's the first half of the equation. This is our line integral. And that little circle on the integral sign, super important. It just means we're going all the way around a closed loop C. This whole expression represents that total circulation, or that macro spin along the boundary. And Green's theorem tells us that line integral is, get this, exactly equal to this thing, a double integral. So instead of walking along the curve C, we're now looking at the entire 2D region D that the curve surrounds. This side of the equation is how we add up all those tiny internal spins. Now let's zoom in on that part inside the double integral. That little quantity, the partial of q with respect to x minus the partial of p with respect to y, it actually has a name. We call it the 2D curl. And it's literally the measure of that microscopic spin at any single point. So the theorem is just saying it again. The total spin on the edge equals the sum of all the little microspins inside. See? It all connects.
Okay, that's enough theory. The real magic of Green's theorem isn't just that it's a neat idea. It's that it is an incredibly powerful problem-solving tool. So let's put it to work and see what it can do.
So imagine your professor gives you this problem. Calculate this line integral. And the path is just a simple square from the origin out to the point 1, 1. Looks pretty standard, right? Maybe a little annoying, but doable.
Now you could do this the hard way. You could break the square into 4 sides, parameterize each one, calculate 4 different line integrals, and then add them all up. It's a lot of work, and so many places to make a tiny mistake. Or you can use Green's theorem and turn all that work into one single, much easier double integral.
Let's just walk through it. First, we grab our p and q. P is y squared, q is 3xy. Easy. Next, we find the partial derivatives for our 2D curl. The partial of q with respect to x is 3y, the partial of p with respect to y is 2y. So the curl is just 3y minus 2y, which is just y. Now we just set up a double integral of y over our square where x and y both go from 0 to 1. You solve that super simple integral and you get 1/2. Done. Way faster than doing 4 separate calculations.
So that last example showed Green's theorem is a fantastic time saver. But now let's look at a problem where it's not just a shortcut, it's basically a cheat code. It lets you solve something that would otherwise be almost impossible.
Get a load of this monster. You're asked to find the line integral of this thing. Just look at those terms. E to the x squared, sine of y cubed. Yeah, just looking at that should make you a little nervous.
And for good reason. If you tried to solve this directly, you'd hit a brick wall. There is no simple, elementary way to integrate e to the x squared. You're just stuck. It feels like a trick question.
But what happens if we try Green's theorem? Let's find our p and q. P is that whole messy e to the x squared plus y. Q is x plus that ugly sine of y cubed part. Now, watch the magic. Let's get the partials for our 2D curl. The partial of q with respect to x is, well, it's just 1. That crazy sine term just disappears. And the partial of p with respect to y, it's also just 1. The exponential mess is gone.
This is the absolute beauty of the theorem. Our 2D curl, delta q over delta x minus delta p over delta y, is just 1 minus 1, which is 0. All of that insane complexity, it just vanished into thin air.
So what's the double integral of 0 over any area? It's always 0. We just solved that complete nightmare of a problem, and the answer is just 0. That's the real power of this thing, turning the impossible into the obvious.
So the big takeaway here is that Green's theorem isn't just another formula to stick on a flashcard. It's a strategic tool. The real trick is knowing when to pull it out of your back pocket. Here's your mental checklist. First off, are you looking at a line integral over a closed loop in 2D? If so, Green's theorem might be in play. Now for the strategy. Does the integral look nasty? Like really complicated? That's a huge red flag. Finally, and this is the pro tip, do a quick mental check of the 2D curl. Do those partial derivatives make the functions simpler? If the answer is yes, then Green's theorem isn't just an option, it's probably the best path forward.
And that leads us to a final, pretty cool question. We've seen how Green's theorem connects a 1D boundary to the 2D area inside it. So, what happens if you go up another dimension? What theorem connects a 2D surface, like the skin of a balloon, to the 3D volume of air it holds inside? Well, thinking about that question will lead you straight to the next two giants of vector calculus, Stokes' theorem and the divergence theorem. But that's a story for another time. Thanks for watching.